Hey everybody, Jeremy Blum here with another Arduino tutorial. As you can tell, I'm outside talking to myself like a crazy person. That's because this week we're going to be focusing on using GPS. So I've got my GPS tracker here. I'll show you guys what it looks like later, but this is the antenna sticking out the top. And I'm in Washington Square Park in New York City right now. So what we're going to do is we're going to walk around, see what kind of data we can grab. We'll put it on the SD card, and then we'll be able to generate a map of where our GPS logger has been. So let's go for a walk.
As you just saw, in this Arduino tutorial, we'll be talking about how to interface the Arduino with a GPS module. GPS, or Global Positioning System, is a way to get real-time information about your latitude and longitude and altitude from satellites. So, we'll specifically be using the Arduino Mega, the Cooking Hacks GPS Shield, and the Cooking Hacks SD Card Shield. So I've used this one before in my data logging tutorial. Go ahead and watch it if you haven't already. What we'll be doing is using our GPS antenna to get real-time location data and save that information, specifically latitude and longitude, to a comma-separated values file on our SD card. We'll be using the tiny GPS Arduino library to help us parse that data, and then what we'll do is we'll be able to put the SD card in our computer, grab the latitude and longitude information off of it, and use a service like Google Fusion Charts and Google Earth. I have one of the Google Earth charts and maps up on the screen behind me to take that latitude and longitude data and turn it into a map overlay that shows us where we've been over the course of that day. I chose to use an Arduino Mega for this because I wanted a serial port to use the GPS shield with. GPS transmits data in a standard format at 4800 baud into a serial port, but I wanted to also be able to use a serial port to do debugging on the computer. You can do this with an Arduino Uno. You can either choose to disable debugging to the computer and use that serial port to interface with your GPS, or you can use software serial, which is a library included in Arduino, to interface with your GPS module. But since I had the Mega around and I wanted to make it as easy as possible for me to communicate with both at the same time while I was debugging the system, I chose to use the Arduino Mega. You'll also want to make sure that you have a 9-volt battery and some kind of power switch so that you can make this thing portable and carry it around with you. I also recommend getting some kind of case. I repurposed a case from a logic analyzer that I have. Carrying this thing around New York City outside, I didn't want anyone to be stopping me saying I look suspicious, so I thought it was a good idea to put this in a case. Okay, let's start by taking a look at some of the history of GPS and kind of how we got to where we are today, and that'll help give us a little bit of explanation for how we're going to use the GPS system to get our latitude and longitude data onto our Arduino. GPS stands for the Global Positioning System. It was initialized by the US Department of Defense in the 1970s, originally for military purposes. However, President Ronald Reagan issued a directive making a degraded version of GPS available to civilians in the early 90s. This, however, still was not very accurate. Bill Clinton later signed a bill making the 20-meter full-resolution version of GPS available to civilian users around the year 2000. The system today is still maintained by the US government, but is accessible by users worldwide. GPS systems require unobstructed line of sight to 4 satellites in order to function. All GPS satellites constantly transmit the time and the current position above the Earth. They use code division multiple access, the same technology employed by some cellular carriers, to allow multiple satellites to communicate over the same channel simultaneously. Since we know the speed at which electromagnetic waves travel, the speed of light, 3 times 10 to the 8 meters per second, the position of our receiver can be calculated by analyzing the differences in the time it took for the signal from each GPS satellite to be received. Ordinarily, 3 satellites would be enough to triangulate our position, since we live in 3D space and are presumably on the Earth's surface, but 4 or more are generally required in order to compensate for timing errors. Even a several microsecond offset in a satellite's atomic clock, when multiplied by the speed of light, can result in wildly inaccurate positioning information. A three-dimensional version of the distance equation, which people are probably familiar with from geometry courses, with added biasing for some time offsets, is used to calculate position. The GPS receiver that we'll be using today, as well as most GPS receivers, uses the NMEA 0183 serial communication specification. The spec designates the typical baud rate, 4800 baud, and the message format. Knowing this format, we'll be able to decode the data string that we receive in serial into time, latitude, longitude, etc. The formatting of this string is pretty ugly, and there's multiple ways to analyze it, so I won't go into all the details because we'll be using the Tiny GPS Arduino library to do most of that decoding for us. If you're interested in the content of the string, you can look at the raw value coming in over the serial connection, or you can look on Wikipedia at all the information that can be contained in that string. In addition to receiving information from the GPS, you can also send requests to it that tell it what kind of data you're interested in receiving. There's multiple format types of strings that will contain different GPS information, and you can choose what you want to receive over the serial interface. Our hardware setup is as follows. There's an Arduino Mega with an SD card shield mounted at the top. It's plugged into the in-circuit serial programming header, which is basically just SPI pins. And I've also connected the slave select pin to pin 53 on the Arduino Mega, as that's the default slave select pin in the software. The GPS shield is connected to one of the Arduino Mega's extra hardware serial ports. In this case, it's UART number 3, so TX3 and RX3, making sure you put it in the proper orientation so that TX on the GPS goes to RX on the Arduino, and vice versa. Make sure you also hook up power and ground on the GPS shield. I've also added a battery, and I've put a switch in line with the battery in order to enable me to easily turn the system on and off. First things first, we'll need to get our SD card set up, and we'll need to download the Tiny GPS library. If you're on Linux or Mac, it's a similar operation. You can do it from the terminal. Just Google how to format an SD card. On Windows, you'll right-click on it, hit Format, choose FAT. You want it to be FAT16, and the default allocation size is fine. You can change the volume label. I changed mine to GPS if you want. It'll tell you it's going to erase all the data, and you're all done. Now we want to add a file to our SD card that will actually be logging the data to. So make a new file. You can do this in the Linux or Mac command prompt by using the touch command, or you can do it on Windows by just making a text document and changing the extension. Is pretty easy. So I'm going to call it capitallog.csv. Make sure you change the extension to .csv because that's what our code will be expecting later. CSV is a comma-separated values file. It's the easiest way to get it uploaded to things like Google Maps to overlay image data. Okay, that's perfect. You can eject the SD card and put it into your Arduino. Next up, we want to make sure we get the Tiny GPS library. Go to this web address, I'll link it as well, and go down to the download section to download the zip of the library. I've already gone ahead and downloaded this, so I won't download it again. But once you've downloaded it, you'll want to put it into your Arduino program directory. So in Windows, it'll be wherever you installed Arduino/libraries. Extract the Tiny GPS folder, and it should go in there. It should look something like this with the examples and the C++ and H files. Once that's in there, then you can go ahead and open Arduino, and we'll load up one of the example programs to see if we can get our GPS outputting some data. So go ahead and open up the Arduino programming environment. Once the Arduino programming environment is open, go to File, Examples, and we'll go to the Tiny GPS example. So we're going to choose the Test with GPS device option. And there's already some nice sample code here that's written that will grab the data from the GPS and spit it out over the serial connection to our computer. We're going to make a few minor modifications to it though. Like I mentioned before, we're not using software serial for our connector. I chose to use a hardware serial connection. If you're using an Uno, you'll just keep the software serial and set the ports up right here for which one is RX and TX. But for us, I'm going to change it to hardware serial. So I'm going to remove the inclusion of the software serial interface. I'm going to remove the declaration of the software serial object. And you can see here is where we're setting up the new soft serial interface. It operates at 4800 baud, like I mentioned, with our GPS module. I'm just going to do a find and replace for all NSS with serial 3, because that's what we're hooked up to. So that'll change it to using hardware serial. So I'll hit replace all. Okay, and we can see that it's been changed to serial 3 there in all the places where it's doing that. So before we actually load this code on, let's take a very quick run through it. I'm not going to go through all the details, but basically at the beginning it's printing out some header information so you can see what you're going to be looking at. and then it goes through a loop and it prints out an update every 1 second. The GPS dump is where it gets the actual data from the GPS, and it's using some built-in functions from the library to do that. What we're going to care about the most later, and where we're going to make modifications to this program to log to the SD card, is the GPS dump function. So this is calling various functions from the library that get things like altitude, the course, the speed, things like the float versions of latitude and longitude, the number of satellites that we have connected, all kinds of good information, and then printing it out on the screen in a pretty format. And so we'll grab this information later, modify it a little bit, and put it in a friendly format for putting into a CSV file that we can then get on the web and use to overlay some data from our GPS trip. There's a couple of helper functions down here like print int and print float that allow the library author to more prettily print the information that we're getting to the serial monitor, which is nice. It just looks good. But this is all, like I said, mostly for kind of debugging purposes. So this is what we're working with. We didn't have to modify too much. Let's go ahead and save this file as a new file because we can't save over the example. So go to File, Save As. For now, I'll just put this on my desktop, and we'll call this GPS debug. OK, so we'll put that on the desktop, hit Save. We're good. OK, now make sure you have the right Arduino and port selected, and upload it to your Arduino. I already have mine connected. Once it's done uploading, open up your serial monitor. OK, and we'll see on the serial monitor that it's printing out some information for us. It's printed out that header that I showed you earlier, and it's printing out all these stars. That's because there's no valid satellite fix. However, we do know it's working because the charge received is talking about the charge that have been received from the GPS unit. So we can see that it's increasing with time, which means that the GPS unit is transmitting information to the Arduino that we can then use. Naturally, I'm filming this video inside. I'm not outside, so I don't have a satellite fix. In the beginning of this tutorial, when I showed you outside, the GPS had already gotten a satellite fix, and I was walking around with it, obviously. When we modify the sketch, we'll add an LED indicator that shows us when the satellite actually has a fix, so that when you're not next to a computer that you can debug it, you can confirm that this data is in fact getting filled in. OK, so we do know it's working. It's definitely receiving data, and we're not getting anything because it's not valid, but that's just fine. When you do go outside, it's suggested that you put some kind of plastic enclosure over the antenna. It should help it get a satellite fix a little bit sooner. And you shouldn't be surprised if you have to walk around or stand still for a couple minutes before it does actually manage to get a satellite fix. And this will vary with different GPS units and things like that. OK, so we have our example sketch working. It's not showing us anything too interesting right now, but I'll use some sample data later to show you what we might kind of expect to get here. The next thing we'll do is take our GPS debug program and modify it so that it saves data to the SD card in a format that we're interested in, and so that it turns an LED on when we have valid data, so that we know when we're walking around outside if we're actually gathering valid satellite latitude and longitude data. So let's get started on doing that. Now that we know our GPS is working properly, we can go ahead and get it outputting data to our SD card as well by modifying this sketch. I recommend first that you save this sketch as a new sketch so that we don't overwrite our example code. So I'll save this one as GPS logger. OK. So we hit save. We're good to go there. Let's include some other necessary libraries that we'll need. Of course, we're going to need the SD card library so that we can write to our SD card. I'm also going to include the standard library so that we can do some string manipulations and things like that that require it. So that's standard lib.h. You should also modify your comments, of course, always to make sure they're up to date. This is no longer up to date. This requires the use of a second serial port and assumes that you have a 4800 baud GPS device hooked up on serial 3, which is more accurate. All right, so we're already defining the tiny GPS object here. I also want to go ahead and define some other important things that we'll be using. First thing is a static char that we're going to use as a character buffer to hold string data as we're processing it. So a buffer is just, you can kind of think of it like a temporary holding place for information as we buffer it in from a receive line or something like that. So you'll see where we're going to use this a little bit later. So that's static char d2 strf buffer, and we'll use this a little bit further down the line. I'm going to make it 20 right now, which means it can hold up to 20 8-bit characters in it. And this is statically defined because of the way we'll be using it a little bit later, which I'll show you. I also want to choose our SD card pin, so that's going to be CS equals 53, because that's the pin that I showed you earlier that I had hooked up to the SD card interface chip select pin. We don't really need to define the card tech pin because we're not going to use that, but we should define our LED pin because we're going to use that for some debugging. I'm just going to use the onboard LED, which you should all know is already hooked up to pin 13. Okay, so that's that. The next thing is I want to define some strings that we're going to use to hold information that is coming in about latitude, longitude, and date time. So this will be like our global variables that are at any given time have the most recent latitude, longitude, and date time information that will then output to the SD card. I want to define these globally because I want to be able to update them in the called functions, and then in the main loop, I want to use them to write to the SD card. So we're going to define them up here. So we'll make the first one string SD date time. So the first string will have the date and time in it. And I'm going to initialize these all to invalid values. And the reason why I'm doing that is because, as you saw earlier, when you're inside, you don't get valid values. So we want to make sure that on the SD card, we're not just outputting garbage. We're going to actually write the word invalid to that entry in the SD card CSV file if we don't have a satellite lock. And that'll make it really easy when we're going through later to just delete the lines from the CSV file that we don't care about and only graph the ones that we do care about. So I'll do this for all of them. So we'll do latitude and longitude too. Okay, and that's all really the information that I care about. You could get other information like the number of satellites and stuff like that, but the only stuff I want to save to our SD card is this for right now. So I'm going to write one more string here called data string. And the data string is basically, I'm going to start it off empty. We're going to concatenate the values from these three guys into the data string with commas in between it, like I mentioned earlier for comma-separated value files. That will then actually write to each line on the SD card's log file. So this is the data string that will actually fill up and use to write data correctly. Okay. All of our function definitions are still fine here. They've just defined them at the top, and then they're using them at the bottom. These are called function prototypes. Okay, the next thing we'll want to do is in our setup, we already have our serial and stuff set up, but we're also going to want to make sure that we set up our chip select pins and our LED debug pin to be outputs. So we all, of course, know how to do this already. That's pin mode CS output. Oops, I have to spell pin mode correctly. And pin mode LED output as well. So those are both set as outputs now. Again, add comments. Comments are your friend. So this is the chip select pin for the SD card. And this is the LED indicator. These are our serial interfaces. This is where we're outputting debug information to the screen. Now, before we do that, I want to make sure it connects to the SD card and is working properly. So let's connect to the SD card. And this is all taken directly out of my tutorial on doing data logging. I copied the code pretty much straight out of there. So go take a look at that if you haven't already. So the first thing we're going to do is going to say if it can't begin a connection to the SD card, we want to throw up an error and have the system not work, because then we're not going to be getting anything, and that's no good. So make sure you declare the chip select pin. So it's going to try to begin a connection on that chip select pin with the SD card. And so if it will do it, this will do it. But if it can't for some reason, then we want to have it kind of fail and cancel the program, because then it's not worth doing anything else after this point. So we'll print some debug information to our terminal in the event that a computer is connected, in which case we'll say card failure. This will help us to debug issues if we run into them. And we're going to enter a return here, which basically just kills the program where it stands. All right, the next thing we're going to do is basically leave the setup the same here. This is all still fine to print to the display. We'll keep printing the information. Since Mikael Hart originally wrote the library, it's nice to keep his name in there. Or you can remove it, do whatever you want. It's up to you. And now we're going to go into the loop. Okay, so we're going to have to modify the loop a little bit so that we can, in addition to printing data out to the screen and creating the GPS, we also want to use the loop to write information to our SD card. And like I said before, we have this GPS, this feed GPS and GPS dump functions that are grabbing all the information from the GPS to the functions below here. I'm not going to go into the full details of how they work, but it's grabbing all that information and then it's printing out the serial. We're going to add information to these functions down here that save the current latitude and longitude to those global variables we defined earlier. So if those are updating those global variables, then when we exit the functions after calling them from GPS dump, then we'll go to the next part of the loop, which will be to use those values that were just updated and to print those out to the SD card. So right after GPS dump, we're going to write the newest information to the SD card. Okay, great. So I already mentioned this before. We made that data string, and this is going to be a concatenation of all the values. So we'll go ahead and actually add the capturing for those values in a minute, but for right now we're going to assume, okay, those values, the latitude, longitude, and date time have just been updated, and we now want to concatenate them all together into a comma-separated format and put those onto the SD card. So the first thing we need to do is actually concatenate them. So to do that, we'll put them all in there. We'll use the plus sign for concatenating strings, and make sure you put commas in between them. So this is grabbing the date time and then putting a comma after it, and then we're going to add the SD latitude, and then after that we're going to put another comma, and then after that we're going to put SD longitude. So this is precisely what's going to be written to the next line, essentially, on our SD card. And we'll use a print line statement to do that, so it does put a new line after it, so we have one entry for each second that we're grabbing data, because this is updating once a second. The next thing we're going to want to do here is update our status indicator LED. So again, we'll get down to this in just a second, but like I showed earlier, I was setting these to invalid when we don't have valid data. So we can actually just look at these strings, see if they're still set as invalid, because that would mean that when we add them to the functions down here, it hasn't updated their values. And if they're invalid, we want to keep that LED off. And we'll just turn that LED on when they're grabbing valid data. So if they're ever being saved as invalid, then we know we don't have a satellite lock and our GPS unit isn't doing anything. So let's actually check that using an if statement and a string compare. So SD date time, and we only really have to check one of them, because if one of them is invalid, all the other ones are going to be invalid. So we'll just check date time, that's fine. And if it equals invalid, that either means it's still set as invalid from when I set its initial value to invalid up here, or it means that in these functions down below here, where we're actually updating those values, in a minute we're going to set them so that if they are getting invalid data, it will change this back to invalid. So whenever we have invalid data, we can pretty much be certain that that will say invalid. So we'll keep the light off in that event. So if it's not invalid, which is what I've said here, we will turn the light on. We don't need to put a bracket here because it's only one line. When you're just writing one line in an if statement, you don't need a bracket. So we'll write the LED to high to turn it on. And that will indicate to us that we're grabbing valid data. Otherwise, let's make sure that we set it to off. So digital write, LED, low. Perfect. Okay. So that's great. So we have our LED updating to keep us up to date with whether or not it has a valid satellite fix. The next thing we're going to want to do is open up our data file so that we can actually write to it. And again, this is right from my data logging tutorial. So we're going to open the data CSV file. To do that, we're first going to make a new file type. So we're going to type in, so we're defining an object here, file, data file, equals sd.open. And remember, we named it earlier when we set up our SD card, capital log.csv. And we're going to open it for writing, so we use the file write definition. Again, this is right from my other tutorial. Okay, so we have that set up for writing, and now what we're going to do is actually make sure that it opened successfully. And if not, we'll print an error out to the debug. So if data file, so this will be true if it was opened successfully, data file, not fail, then we want to print the newest string to it, this data string that we concatenated right up here from all the data that we'll be getting. So we define our object as data file, so we'll write data file dot println, and we're going to write the data string that we just concatenated together. Okay, and print line is ensuring that we're putting a new line after it. So there'll be one entry in each line of the CSV file that has date, time, latitude, and longitude. And for debugging purposes, in addition to writing it to the SD card, let's also do a serial print line out to the computer so we can see not only the nicely formatted data, but the format of the data that has been written to the SD card. So when we're debugging, as we're testing this, we'll be able to ensure that it isn't, in fact, writing the data format that we expect to the SD card. And then we'll close the connection, just like I did in my previous data logging tutorial. Now, if we couldn't get a connection to the data file, the file's not there for some reason or something like that, we want to make sure we're aware of that. So let's put in an else statement that tells us about that potential issue. And in that case, we'll just write out to the debug terminal, serial.println. I'm going to put a new line here so that it doesn't go on the same line as something previous. \n just puts basically an enter or a carriage return before whatever you're typing. And I'll have it tell us couldn't open the log file. All right, so now we'll know if something went wrong there. So we're making great progress. So now we have all of our strings set up, and in the loop, every second that it would normally just be outputting to the print line display or a terminal monitor, it's also going to open up the SD card, concatenate together the most recent information about the GPS, indicate whether we have a satellite fix or not by determining whether that data is invalid or valid, and then it'll write that data to the SD card, which we can then use after to make very pretty maps. The next thing we're going to do is investigate a little bit more closely this GPS dump function and look at all the places where it's grabbing data we want, go look at those functions and add some code in those functions that's going to allow us to extract the latitude and longitude data that we care about in the quickest and easiest way possible. Okay, so looking at GPS dump, let's see if we can identify the things that we care about. The first thing it's writing is the number of satellites, and then it's printing a whole bunch of information, things like altitude and course that we don't really care about that much. What we care about are a few things. We care about the actual latitude and longitude, so we can see that it's getting those from gps.fgetPosition, and we're also going to care about the date and time. So in terms of things that we actually care about, we see it has this function print float that's printing out the float in a pretty format. So this is our longitude right here, or sorry, our latitude. This is our longitude. And you can tell because flat is float latitude and flon is float longitude. And so they're actually grabbing it from some functions that are built into the GPS library and calling the print float function to print them out to the screen. So they're not being printed right here. The function is printing them to the screen. We also, of course, care about the date, which is actually should more accurately say it's date and time. So this is the date and time. So looking at this carefully, we can see that in the print float function, we're going to want to go into the print float function, and if we're trying to print out latitude, also save it to that global variable that will then get written to the SD card. Same thing goes for longitude, and we'll look at the print date function in order to kind of steal the data for the date and put it onto the SD card global variables that we'll be using as well. So let's first go take a look at print float, because that's being used for latitude and longitude. And we'll only want to modify it for when it's being used for latitude and longitude printing. Okay, so print float, we can see that it takes in a value, which is the actual latitude and longitude data that it's grabbed from the GPS library, whether or not it's invalid, the length of the information, and the precision. So what we're going to do here that's going to be kind of sneaky is we're going to add another argument to this function that allows us to determine if we're trying to get latitude or longitude data. We'll add another thing here called another integer, and we'll call it sdval. And this will kind of determine what we're actually trying to grab. So up back here, what we'll do is we will add another thing that we can pass in. So after that other information, after those other arguments that we see, we can add another entry here that tells us what we're trying to grab so that we only try to output that to the SD card for that particular information. So when we're printing the longitude, what we'll do is we'll make that a number 2. And when we're printing the latitude, we'll make that a number 1. And so what this will accomplish is we'll know what kind of information we're trying to call, and we'll only output at the SD card if it's the particular information that we care about. Now, one more thing. Remember, they have function prototypes defined up at the top here. So we're going to make sure we want to update these as well. So SD val, that's an integer, and SD, well, it's just for print float, I guess. So we'll update that. Now, also importantly, anything else that's calling print float, you can't just leave that empty because the compiler will be unhappy. So let's just put in zeros here. So if it's a 0, we're just going to not print anything to the SD card. So these are all using print floats. Okay, I think that's all the places they're using it. We can use a search to make sure. And it looks like we got all of them. Okay, so back down to the actual function. Let's modify it so that if it is a 1 or a 0, it outputs the correct value to that global variable that we care about. So let's see if we can figure out how this is actually working. It's defining a char array, which is essentially just a string, a bunch of characters strung together. That's 32 long that it calls SZ. If it's been told that the information it gets is invalid, and again, this is coming from the library, it will print out those stars, which we saw on the print line debug display earlier. So it's printing out all those stars if it's invalid, fine, and it's saving that. It's doing a string copy, so it's putting that into the SZ variable. Now that's all well and good. We want to make sure that if it's invalid, that like we defined earlier, it sets our SD card value to invalid as well. Or just stars is fine as well, because we're only checking invalid for date time, so we can kind of set latitude and longitude to whatever we want. So we can see it prints out SZ here, so that's where it's actually printing it to the display. So in addition to doing that, if the SD val is 1, and remember that was latitude, so if SD val is 1, then that means SC is currently holding the information about what the current latitude is. So we want to save that to that global variable. So we say if it's equal 1, then we want to say SD lat equals SC. So we're just literally setting it to all stars. Again, doesn't really matter. It just shows that it's invalid. The only one we're actually checking whether or not it's invalid to turn on the LED is date time. So we have to make sure that that says the words invalid instead of just stars. But for this is fine. So otherwise, or else if you will, if the SD val that we have input into this function is equal to 2, then we know we're dealing with longitude. So we want to say SD long equals SC. And if it's anything else, it just won't do any of these. So if it's 0 like all the other ones, then it won't be writing anything to the SD card, which is exactly what we want. Otherwise, this is when val is valid. So this if statement was when it has invalid data or it doesn't have a satellite lock. When it is valid, we want to make sure that we're writing the information that we want to our SD card. So this is going to get a little bit more complicated, and this is why I imported that additional library earlier. So what we have to do here is deal with the fact that value is passed to us as a float. So it's a decimal number representation. But what we're printing out to the screen is we want to concatenate strings. So not only do we need to just grab this float, we actually need to convert it to a string. And that's why I imported standard lib earlier. So let me write it out first, and then I'll explain exactly what it's doing. Okay, so let's investigate kind of what's going on here. I won't get into the complexities of what he's doing down here. This is just making it formatted and look pretty to print out evenly on the display. We don't really care about that. What we do care about is grabbing this value of val and making it a nicely formatted string. So I imported standard lib up at the top of this program. Let's take a look on the C reference online to see what d2strf is doing. So if we look online at the online documentation for C, this function converts a double passes a val into an ASCII representation that will be stored in S. So if we look at the actual parts of it, we can see here that these are kind of all of the parts. So we have this val, which is a double or a float number, the width, and the precision. So the width is basically determining the maximum number of digits before the decimal place, and the precision is referring to the places after the decimal place. And then the string is that buffer that I was talking about earlier that is basically being used as sufficient storage space to hold this as we do the transfer. So what's happening here is we're using that buffer that I defined up at the top, which is more than long enough. I think I made it 20, and this is 10, up to 10 total, and then 5 after the decimal place. And so this is taking the val and converting it to a string that we have as sdlat. So this function will save it into this global variable, and then in the main loop, we'll call this global variable and concatenate into a string that we can put on the SD card. And then we do the same thing if the value is 2, except we're saving it to the longitude value. So that's it for that. It's very, very simple, not too complicated, and it easily allows us to turn the float into a string. All right, so we really just have one more major thing to do here, which is to deal with the date. So we saw earlier that it was using this function called date to print out the current date that it's getting from the satellite. So if we go down to print date, we're going to have to make a modification here as well. This function is only being used to print the date, so we don't have to add another argument to determine when we're being called into it. But what we will do is handle printing. So here it's clearly printing. This is the invalid string, all those stars. What we're going to do is add a function in here where if it's invalid, we save sd date time to invalid, as I defined earlier. And remember, whenever sd date time is invalid, that means you don't have a satellite lock. It also means the LED is off. So it's either initially defined to invalid or it gets set invalid in here when it does not have a satellite lock. So that'll handle that state correctly. And now we also have to look at what it's doing when it does have a satellite lock. How is it printing the date, and how we can kind of steal that to put it onto the SD card. So the way we'll do that is we're going to rely on another function here. So if we look at the else, so this is when it is valid, it's again using this sc here, and this is printing out all this information. It's basically all this %02D is formatting each month, day, year, hour, minute, and second into a certain decimal format and printing it out into a string on the display. So, and then it's saving it into SZ for us. So that's convenient for us. It makes our job pretty easy. All we have to do is grab that SZ for ourselves and put it onto our SD card variable. So SD date time equals SZ. And that should be it. So that's grabbing all of the date time values and putting into that SZ variable. And now what's going to happen is back up on the loop. If we go look at the loop again, where every time through the loop it does the GPS dump here, which updates those global variables, and then we grab those global variables in here, write them to a data string, and output those onto the SD card. And that's it. We're basically just hijacking the functions of this example script, make our life nice and easy, and grab all of the SD information from the existing printline debugger info. So go ahead and save your file and get it uploaded to the Arduino, and let's take a look at what is happening. Make sure you have your SD card in too. And of course, I have a stupid issue here, SD date time. And there should be no space before the exclamation mark and the equal sign. SD lon should be LON. This needs a bracket because it's 2 lines. Once you've corrected all the stupid errors that I made, and you upload it to your Arduino, you should open up the serial monitor, and we should be getting not only the pretty debug info, but also each line should also have the information exactly it's being saved to the SD card. And we can see that we are indeed getting that. So we're getting invalid for the date time, and then stars, and these are comma-separated values, so that should work out just great. So now let's actually close this and load up the SD card into our computer. So take the SD card out of your Arduino, pop it into your computer, and let's make sure that we're actually getting the data saved to the SD card. So I'll open up that file. Yes, and we can indeed see that, I mean, it's not useful data because I don't have a satellite fix, but we are getting the data written to the SD card exactly as we would hope it to be. Perfect, good job. So now we have our GPS unit, and it's logging the data to our SD card. The next step is we're going to take this data, obviously go outside, walk around, turn the GPS on. It'll turn the LED on board when it is indeed connected to a satellite to make it easy for you to tell. And then we'll start to gather some data. And I've already gathered some example data, which I showed you at the beginning of this video. And now I'll show you how to take some example data that I've already taken and get it up on Google Maps or on Google Earth to plot it out. Once you've gone around and acquired some awesome data, go ahead and open it up on your computer. I have some sample data that I took in Washington Square Park in New York City, walking around. So go ahead and open that up. That's what I have here. I've already gone ahead and deleted the invalid row entries because those are obviously not useful to us. I'm going to insert an additional column at the top that gives us some more information and tells us what each column is. So date/time, latitude, and longitude. And this will just allow us to import it more easily into Google Fusion Charts, which we'll do in a second. So once you've done that, do a save as with headers. Okay, make sure you keep it as a CSV file because that's what Google will understand. Hit yes to replace it. Hit yes again, and close out of that. Next, log into your Google account. As of right now, this is beta functionality that only works with default actual Gmail accounts. You can't use it on a Google Apps domain yet. Go to your Google Drive up here, and then click on Create. Go to More, and choose Table, which is a beta option. Next, you'll choose to upload a file from this computer. We can see that it wants CSV files. We'll choose the one that we just did with headers. Hit Open. All the default options are fine. Hit Next. Okay, and we can see it's imported the table quite nicely. The column names, which we just added, are in row 1, which is correct. Hit Next again. You can name this something. So this is a test of my GPS. We can allow it to export, that's fine. If you want to add an attribution link, do that. Otherwise, this is all good. So hit Finish. Okay, and we can now see that it's imported the entire table into Google Drive, into the Fusion Tables beta program. So now, this is actually surprisingly easy. Hit Visualize, choose Map. It automatically figures everything out and will map it for you instantly. It zooms out very far for whatever reason, but I can zoom in here. And sure enough, this is all the data. So if you're watching the video at the beginning, I started recording sitting on a bench over here, walked over to, or I started recording GPS data over here, walked over here to the fountain. This is where I started filming. Then that sped up portion that I showed is me walking around here like this. I got back to the fountain, turned off the video camera, and then walked to the nearest intersection to start heading home. And that's basically it. This is imported. You can do whatever you want with it. You can do all kinds of cool stuff. I won't go into all of it now. One particular thing I will say is that you can download the KML. The KML is something that you can import into Google Earth. And if you notice at the beginning, I showed a virtual fly-through of what I was doing. So I can export this KML file, and then if I want, I can go open up Google Earth and open up this KML file and do a visualization of it in Google Earth, which is actually pretty neat. I won't go into all the things that you can do with it from there. There's quite a bit, but you can definitely go experiment with this. You can do things like attach photos to the different locations, things along those lines. You can also just go to File, Open, and look at the data set that we just exported. So I put mine on my desktop. So this is my test. Hit Open. It'll add it over here and zoom on into it. And sure enough, there's our test data. You can see actually two of mine overlaid on top of each other because I've already imported this before. So I'll turn this one off. There we go. So that's what we just imported. You can mouse over each one. It'll tell you the time, the latitude, and longitude that you were at that particular location. And you can make all kinds of adjustments to it and do fly-throughs and stuff like that. So that's it. That's how you grab GPS data, how you log it to an SD card, get it on your computer, and do some really awesome visualizations. Thanks for watching my latest Arduino tutorial. I hope you guys enjoyed it. Don't worry, I am working on more of them. I'm sorry, but they take a really long time to put together. I'm sure you understand. As always, you can get all of the schematics, source code, sample data, etc. on my website, on element14.com, and on the links in this YouTube video. You can also find them on my GitHub page. If you need to get in touch with me, the fastest way to do so is through Twitter. My username is SciGuy14, same as my YouTube username. And if you haven't already, go check out my recent tutorial series on Eagle, which teaches about schematic design and PCB board layout. Okay, thanks again for watching, and I hope to see you guys soon. Thanks to Element 14 for helping me to sponsor this video series. They were kind enough to provide a lot of the materials that I'll be using to create these tutorials. Feel free to go visit their website at element14.com. Check out their community, which is a great place to talk to people about electronics, the Arduino, and basically anything else engineering related. And they also have a store where you can buy a lot of the parts that we'll be using in these videos.